So picture this. It's the years right after the 1986 Challenger tragedy, and for NASA, there is absolutely zero room for error. I mean, every single piece of the space shuttle was being put under a microscope, re-examined, redesigned, retested. This is a story about one of those components, about a problem that honestly looked like a disaster waiting to happen, and the incredible detective work it took to find out if the danger was even real. All right, let's get into it.
And that right there, that was the billion-dollar question. I mean, you've got the safety of future astronaut crews literally on the line. So these engineers had this massive task of separating what was real from what just looked real. Was this critical redesign secretly making things worse? Or were they just chasing a phantom in the numbers? This is all about how you make those life or death calls when the data isn't as clear as you'd hope.
Okay, so to really get what's going on here, we have to go right back to the source of the problem. The Challenger accident, as we know, was traced back to a seal failure in one of its huge solid rocket motors. So naturally, a massive engineering effort kicked off to create a brand new, much safer design.
First things first, let's get our acronym straight. The original motors, they were called SRMs. The new and improved ones were the RSRMs. That's for redesigned solid rocket motors. Now the goal for the RSRM was simple: make it more reliable, make the shuttle safer. But, and you knew there was a but coming, early tests on this brand new design raised a very serious red flag. And it all came down to something called pressure oscillations.
Okay, so what is that? Well, think of that giant solid rocket motor as a massive, powerful candle. As that fuel burns, it's not perfectly smooth. It creates these vibrations, this kind of intense shaking inside the motor. Now, a little bit of shaking is totally normal, but too much? That can put some seriously dangerous stress on the entire space shuttle. It's something engineers watch like a hawk.
So, as you can imagine, when the test data started rolling in from these new, supposedly safer RSRMs, the first thing engineers did was compare it to the old data from the SRMs. And what they saw, well, it was definitely not what they wanted to see.
All right, take a look at this chart. This comes straight from the engineer's analysis. It's comparing the old motors, that's the bars on the left, with the new ones on the right. Just look at it. At every single point in time they measured, the bar on the right, the new RSRM, is higher. This wasn't some random fluke. The data was showing a very consistent and very worrying trend.
So this was the terrifying question just staring them right in the face. Is it possible that in fixing one fatal flaw, they had accidentally created a brand new one? I mean, just looking at the chart, the data seems to be screaming yes. But, you know, in the world of high-stakes engineering, you just can't afford to trust your eyes alone.
The engineers knew they had to go deeper. Was this difference they were seeing a real physical change in how the motor worked? Or was it possible that it was just random variation, a statistical fluke? To figure that out, they had to move beyond pretty charts and bring out the heavy artillery, rigorous statistical analysis.
And this is the absolute key difference. Our eyes see a pattern, and our brains immediately jump to a conclusion. Statistics makes us slow down and ask a much tougher question. What are the actual odds that we'd see a difference like this just by pure chance, even if the two motors were actually the same? Answering that question took a careful two-step process.
So, here's how they did it. First, they ran something called an F-test. You could think of this as just checking if both sets of data are kind of equally messy or spread out. Once they knew that, they could get to the main event, the t-test. The t-test is the tool that lets you decide, officially, if the average of one group is truly meaningfully different from the average of another. It's like putting all the evidence on a super precise scale to see if it really tips one way.
Okay, so the method was set. The engineers ran the numbers. And you got to imagine, the entire program is basically holding its breath. Did their brand new multi-billion-dollar rocket motors have a secret, dangerous flaw? Well, the result was not what anybody saw coming. Now, they set a really high bar for this. The gold standard in science is usually a 95% confidence level. What that really means is they would only say the motors were different if the math showed there was less than a 5% chance that this was all just random noise fooling them.
And this right here, this is the verdict, taken straight from their report. Just focus on that last column on the right. For every single test they ran, the result is exactly the same, except. Now, in the world of statistics, except means you are accepting the default idea, the null hypothesis, which in this case was that there was no real difference between the motors.
It was a total shocker.
Despite what that first chart clearly showed us, the hardcore math concluded that the extra shaking in the new motors, it wasn't statistically significant. It was, in fact, a ghost in the data. From a purely statistical view, the two motor designs were basically behaving the same. But this is not where the story ends.
Because this is the exact point where pure science meets the messy reality of engineering and keeping astronauts safe. Yeah, the math might say there's no difference, but the engineers couldn't just unsee what their instruments were telling them.
This is a perfect example of what's called engineering conservatism. The statistical test says, hey, don't worry about it, but the raw data consistently nudges higher. When you have lives on the line, you don't take that risk. You listen to the data, even if it's just whispering and not shouting in a statistically significant way. And this chart illustrates their final decision so brilliantly. So look at the light gray bars on the far left. Those were the original safety limits. The middle bars, that's what the limits would be if they only used the new SRM data. But look at what they actually did, the final bars on the right. They pooled all the data together to create a new, higher, and much more conservative safety limit for everyone.
Their solution here was just a masterclass in managing risk. They said, okay, we accept the statistical verdict. The motors are likely the same. But just to be extra safe, they decided to act as if that upward trend was real. So they raised the safety ceiling. That gave them a bigger buffer and a tougher standard to meet for every single shuttle flight from then on.
See, this wasn't about trying to prove a scientific theory in a lab. This was about making sure every flight was as safe as humanly possible. By blending that rigorous statistical analysis with good old-fashioned conservative engineering judgment, they created a new safety standard that protected the program and its astronauts right up until the very last mission.
And it just leaves us with this incredible question that goes way beyond rockets, right? When the stakes are as high as they can possibly get, it's not always about what you can prove with 95% certainty. Sometimes it's about respecting the data, understanding the risk, and making the cautious choice, even if it just means protecting yourself from a ghost.